So the title of my talk is a bit different to the title of the paper. Originally I wanted, the title of the paper is actually different to the title of the abstract. Because originally I wanted to present the new and improved operational semantics for the language QML entirely, but that ran to over 20 pages, so I had to slim it down a bit. So what I'm giving here is an overview of QML and the operational semantics and its implementation in a compiler in Haskell. So QML is a quantum programming language. I don't think I need to justify the existence of quantum programming languages here. It has a structure similar to functional languages and is modeled on the classical language Haskell. So the idea of having a quantum programming language is to simplify the design of quantum algorithms, allow for reasoning principles, and provide a more intuitive understanding. I think Richard Yost said at the previous QPL that the goal of these kind of things is to develop quantum thinking. So QML is a first-order functional quantum programming language, and unlike some of the other proposals for quantum programming languages, it has both quantum data and quantum control. I'll introduce that shortly. Also, unlike some of the other proposals, it's based on strict linear logic with controlled explicit weakening. So, what that means is that we're interested in controlling measurement in QML rather than controlling where things are copied. And hopefully I'll explain that shortly. And the design of the language is guided by categorical semantics. So we looked at the categorical semantics for a classical language and then a classical circuit model. We looked at the analogies to a quantum language and quantum circuit model and tried to develop the language in that way. So the syntax of QML has a simple type system. This is the type of a qubit, and you can tensor qubits together, and there's a unit type as well. It's just a very simple type system used to keep track of variables and qubits. The expressions in the language are either variables. We allow probability amplitudes to be any complex number. Patterns are either variables or pairs of variables. And the terms are pretty standard from any simple functional language. We can have a variable. This one's a bit different. This means we return the variable x, and any variables that are mentioned in y are measured. So that's where our weakening comes in. The units, we have pairs of terms. There's let expression over patterns. And then we have two if statements. And these are our classical control, which is the normal if, and quantum control, the if with the little circle. I'll explain how those work shortly. And we have quantum false and quantum true. And then the multiplication operator that allows you to attach a probability amplitude, complex probability amplitude to a term, and a plus operator which allows you to perform superpositions. So as an example, we can write the EPR states in QML as declare Q false plus Q true. And I've left off the probability amplitudes here because we can infer them to be equal in this case. When you leave them out, QML just infers them to be equal. Simplification. Okay? So, the operational semantics for QML is a mapping from programs in QML into objects of finite quantum computation degree. And this has been implemented in Haskell, and it's available on the project website. You can download it, write QML programs, and run them. Well, not run them, but compile them into finite quantum computation objects. And FQC objects look like this. There's your useful input. The input you want is given as a number of qubits. The useful output is given as B. Any auxiliary input you need and any garbage is produced, and this symbol means that the garbage is measured at the end of the computation. And the mapping from the input tensor the heap to the output tensor the garbage is given by a reversible circuit. And these circuits are represented as simple combinators with sequential and parallel composition, permutations, conditionals, and cubic rotations. That was described in the last QML by Alexander Green. And this can, so the output of the compiler are these reversible circuits with this extra information of heap and garbage and the typing information. And these can be further evaluated to give the denotational semantics, which in the case of when there is garbage and things are measured at the end, it's a super operator, and if there's no garbage, it gives simply an isometry. So it's an example of the operational semantics. We have the pairing of two terms. So we have a term T, which has a context gamma, and a type sigma, and a term U with a context delta, and a type tau. And the pairing of terms is the tensor inflection, and this simply takes the tensoring of the two contexts to the term TU, which has the type sigma tensor tau, as you'd expect. And the term TU in a pair is evaluated to this circuit. So this is the output of the compiler. It takes in gamma tensor delta, and this goes into a copying circuit first. And what this circuit does is, if a variable is used by both T and U, then it makes a copy of it, control not operation on each qubit in that variable to copy it. So what comes out is gamma and delta separate, but they're obviously entangled if they have any shared variables. And then the operational semantics, the circuit for T, is just applied tensor with the circuit for U. So given a T and U and their finite quantum computations, we produce a new finite quantum computation where the heap is any extra auxiliary variables needed by the copying, any variables needed by extra heap needed by T and U, and the output is sigma from T, tau from U, and any garbage produced by those two operations. So we add all the heap up, and we add the garbage up, and obviously the circuit is the output. So a few examples now of how to write terms and how they're evaluated by the compiler. So what happens if we write a forgetful function? If I define true to be if x, then q true, else q true, how does our two different control operators deal with it? Well, what's happening here is we're using variable x. Well, it looks like we're using a variable x, but we're just returning q true all the time, so we're just throwing it away. So the only way to do that is by measuring it by putting x into the garbage. So that's exactly what the classical if operation does. It measures the x, and then depending on the whether x is valued as q true or q false, it does either the first or the second. In the quantum case, then we run into a problem here because we're still throwing x away, so we still end up measuring it. But the way we deal with this is to say that the two branches in the quantum case, if you use the quantum if operation, have to be orthogonal. And I'll explain more about that in a moment. But that means you wouldn't be able to use the quantum control operation for this term. So some further examples. We can define a simple not operation. The not operations take a qubit and return a qubit. And the classical not C, uses the classical control. What this does is it measures x, so if x is in a superposition, it will probabilistically collapse it to either false or true, and then it will only apply one of the branches. And the quantum not is similar, except it's a quantum operation, so we don't have to measure x. And what it essentially does is instant Pauli x rotation. It just swaps the amplitudes on the terms. And q false is obviously equivalent to q true, so that one satisfies the condition again. So using quantum not, we can then define a controlled not operation. It takes in a qubit x, and the output is a pair of qubits. And it's just simply if x, then q true paired with the output of the quantum not on x, else q false paired with x. We can define a simple measurement operation which will measure a qubit just using the classical control operation. And yeah, I'd already given you the PLK earlier, but now I'll show you how these are evaluated by the compiler, what the output is of the operational semantics. For the EPR pair, is the circuit we'd expect. It takes 2 qubits of heap as input, applies the Hadamard on the false, and then applies a control knots operation to output the standard EPR pair. And the measurement operation, it takes in the variable x that we want to measure, it copies it, and then throws away the original and returns the copy. And the fact of throwing it away causes throwing away the original collapses the entanglement caused by the control knots operation, so it gives us classical value. Similarly, the controlled knots operation, this evaluates just to the controlled knot circuit. Not Q evaluates just to the Pauli X circuit, and not C evaluates to this circuit, except this bit is flipped before it's copied. So it gives us the opposite. So I mentioned that to use quantum control, the branches of the if operation must be orthogonal. And this, what's nice about QML is that this doesn't have to be provided by the programmer. It's automatically inferred by the system. And what it does this is it uses some simple axioms to analyze the terms to decide whether they are orthogonal or not. So we have 2 simple axioms. True is orthogonal to false, false is orthogonal to true. If we have a pair of terms, if T is orthogonal to U, then the pair T and some other term V is orthogonal to U and some other term W, because the first 2 components of the pair are orthogonal. Similarly, the symmetric operation here, T and U are orthogonal, so the pair VT is orthogonal to pair WU. A slightly more complicated one is that we can have, if quantum control operations can be orthogonal, and also superpositions, we need to allow superpositions to be orthogonal. And this just ensures that the superposition defines a unitary matrix. So we have lambda 0t plus lambda 1u is orthogonal to kappa 0t to kappa 1u. Unfortunately, it's not quite just as simple as writing these rules. In the operational semantics, these rules need to be interpreted as a circuit that allows us to tell which one of these rules has been applied in order that the circuit is reversible. But I don't have time to explain that here, but in these initial cases it's quite simple. In this case, if it's this case, then we just add a bit which is the identity, and here it's a negation, and then we build it up in the more complicated examples. So I noticed yesterday that nearly every talk gave teleportation as an example. I was a bit disappointed today that no one has. So I added this last night. the teleportation protocol written in QML is it's quite small, quite easy. So we want to teleport a qubit Q. So we define Alice and Bob's qubits to be part of an EPR pair. And then we do a bell measurement on qubits we want to transport with Alice's part of the EPR pair. And then Bob is sent this, it's a result of a measurement of the classical value at home to the QML, we only have quantum bits. So that's moved, the output here should be classical. And then Bob does his correction based on this classical information with his half of the EPR pair. So it's actually not as easy as that, because we have to define what the bell measurement does. And the unitary correction that Bob does is finite. And this is very similar to the algorithm presented by Pablo and yesterday, so also in Sandwich and Pablo. So future work is to extend the QML algebra to include the measurement that was discussed in Pablo's talk yesterday. Extend the orthogonality judgments to try and prove that they're general. So at the moment they're incomplete. For example, we don't allow let expressions to either be orthogonal, which clearly can be the case. And then there's other things like higher order semantics, more difficult questions like that. So there's a project website that you can download to the compiler if you like and play with it and run your own quantum programs. So thank you for listening.
Any questions?
Yeah, you call your language a first order language.
Yeah.
But in the slides I haven't seen any use of it. So are there certain cases where it's a big benefit to have like your teleportation protocol to have like a first order object in your language? Why do you call it a first order language?
What I mean by first order is that you can't pass functions as arguments. It's not high order.
Okay.
So there's the question of if something is not higher order, if it should be called first order or zero order. Did that answer your question?
Just another, what's the benefit for your quantum programming language
Of being
to be completely functional first order?
I'd like it to be higher order, but we don't know how to do the denotational semantics for a higher order language yet. Maybe some people are working on it. So that would be good to have a higher order language. But when you actually run a program, you can simplify it to a first order program. But yeah, higher order is it's a difficult problem. It's taken a lot of work and very much progress. Well, it has to do with some recent progress. Okay.
Any other questions?
I was wondering how you do the flow based on measurement. Like I see how you do the measurement, but then how do you change the control flow with that? Once you've measured into classical, then you said you could change the control flow. Where is that?
So the operational semantics relies on the principle of deferred measurement,
right,
to make it all work. So as long as when you measure something, it's moved into the garbage, and the garbage is measured at the end. So anything that relies on that is also collapsed. So as we copy it, then move one half to the garbage in some cases, or just move the variable itself to the garbage if it's something you're throwing away. So it's measured at the end, so anything that's entangled with it is also collapsed. Okay.
But then how do you use that to apply, say, a different operation, like in the teleportation, for example? I don't know, I didn't seem obvious from the way that the circuit looked.
Yeah, I can't think of an easy way of answering that without going through the operational semantics fully.
Okay, so So let's thank the speaker again.